Beskos, you're going to talk to us about antithetic MLs MC for diffusion.
Multilevel Monte Carlo.
It's yours? Alex.
Okay, thank you very much for the invitation. This is joint work with Yuka Iguchi, Ajay Jasra, and Mohammed Ma. Yuka has done a lot of the theory behind this work. Let's see. So it's a simple idea. It has to do about multi-level Monte Carlo. So this in the context of stochastic differential equations. So something that is important in terms of being able to apply multi-level Monte Carlo for stochastic differential equation is the strong error of approximate schemes for the true solution of the stochastic differential equation. If you start coming up with advanced schemes that approximate the SD, then there are some terms there that they are not easy to sample from, so you lose the extra strong error. But there is this antithetic trick that so you can omit these terms, you can throw away these terms that increase the strong error, and you can use an antithetic idea, some sort of tricks, plus or minus sinuses, and you can recover, when you apply the multi-level idea, you can recover the original strong error of these complicated schemes. Okay, so you throw away some difficult terms, so the strong error goes down. You play around with some plus or minuses, and you recover the strong error when you apply the idea. That's in a couple of phrases everything that is included in this talk. All right, so let me say a couple of things first for SDEs, just to provide some context. So this is the type of models I will be talking about. So there is a drift function here and a number of Brownian motions. So exactly here there's a drift function. It's this one. There's a diffusion coefficient. So there's a lot of effort here done by Yuga to come up with methods that they also apply for hypo-elliptic SDs. So there are some complications there in the proofs, but otherwise the objective is the same, no matter if you have an elliptic or a hypo-elliptic SD. You are interested in an expectation of this type. This is what we call the forward problem in the paper we have submitted. There is some connection with this workshop, in the sense that you can apply multi-level ideas also in a particle filtering setting, and I will show some results. But otherwise, the discussion that I'm going to be showing is about what we call the forward problem. So just this, all right? But there are extensions of these things also in the filtering context, when one is using particle filter. All right, so yes, exactly. So we look at both of, we can cover also hypo-elliptic SDEs. So this guy might be degenerate, and you can express your model like this, for instance. Okay, it's arbitrary, the dimension here, but just to emphasize this fact, so you can have a component here which is 0. Okay, so this is the hypo-elliptic case. Otherwise, there is this guy here. So that's the dimension of my state. It is the sum of the dimension of the smooth component and the rough component. Okay, the dimension of the smooth component would be 0 if you have a regular elliptic SD. It would be non-zero if there is hypoellipticity involved there. All right, let's see. So there would be some operators there involved. They are not. They look a little bit complicated, but they're just standard things that appear once you try to apply the Eater's formula to expand the drift, for instance, of the diffusion of your SDE or the diffusion coefficient. So there is this operator here. So this uses 2 orders of derivatives, and there is this operator here. So it's 1 order of derivative, and this guy will appear in a couple of places. So this bracket operator. All right, the definitions pretty much, nothing more than this. Let's see in practice. So I will I will be playing with STEs and slowly I will be moving into this multi-level setting, okay, and present the contribution there. So I will take things slowly, right? So the talk is much more it's much easier compared to Pierre's talk. I believe.
Info is linear, it's not linear.
Yes, that's true, but the ideas are simpler, I think. All right, so let's see here. Yes, so this could be a non-linear SD, yes, and it could be multivariate as well. So that's the Euler-Maruyama. Otherwise, this is extremely simple. You can use a Milstein scheme, so there are some extra terms appearing here. So there are products, for instance, of the Brownian increments. There is this guy also that appears in this expression. And this is the guy that creates some problems if you want to actually apply this Milstein scheme, okay? So this is a double integral over two different Brownian motions, two independent Brownian motions. It looks fairly simple, but still is not explicit. So you cannot actually simulate from it. So it's nice. The Milstein scheme, it gives you a higher order of convergence in the strong sense compared to the Euler scheme, but you cannot apply it in multivariate setting. All right, unless there is something like this that holds, so unless the diffusion coefficient satisfies some particular condition. So in this case, this term disappears from the expression of the Milstein scheme, so then you can use it. Okay, it's a bit restrictive. In general, one cannot make use of it. All right. So yes. So some definitions that they will play a role when we look at a multi-level algorithm. So there is the weak error, for instance. So here we just look at differences between expectations. So there is this alpha here that refers to the weak error. There is the strong error. So here the two processes are defined on the same space. And there is this beta here. I mean, typically alpha is greater than beta in many discretization schemes. For the Euler-Maruyama scheme, the two things, they are the same. Just to make a comment here, I'm using, if you compare this definition of the strong error here with let's say, a standard book like Kloeden and Platen. So here I'm referring already to the square of the error, right? So it's a little bit non-standard. So in Kloeden and Platen, for instance, they would refer to the square root of this thing as being equal to something. Okay, so let's keep this in mind. All right. So for the Euler-Maruyama, these two things are the same. For the Milstein scheme, we gain something. Okay, and this would have made a difference in the multi-level setting if we were able to actually use the Milstein scheme. All right. Otherwise, we have to do also some Monte Carlo stuff to approximate this expectation. Okay, let's see. So the most of the, if not all of the contribution we have done has been motivated by a paper by Sprutz and Giles, where they introduced this antithetic idea in a multi-level setting. So in their case, they chop off these extra terms from the Milstein scheme, right? And they say, all right, so let's there was an extra term, if you remember here in the Milstein scheme, that suddenly it has disappeared. So this is what they call the truncated Milstein scheme. So that's fine, but you lose one power here. Okay, so the weak error is 1. Before this, the strong error was 2 in the Milstein scheme. Now it got back to being 1 because some terms are lost there in this discretization scheme. Okay, yes. So let's see. So in terms of our contribution, so we look at a different discretization scheme. So we call it the second order weak scheme. Okay, this weak 2 scheme, and it has some terms here. So it looks a lot like the Milstein scheme. There are some some particular quantities. There is this quantity here. There is this tilted quantity here. So we have made some effort here to get an expression that covers both the elliptic, this guy here, and the hypo-elliptic case. Something that maybe I should mention is that at the end, behind this term, there is a second independent Brownian motion that it is involved in these calculations. The whole idea is to make an effort so that the weak scheme it has a higher order of convergence, right? So this discretization scheme has a higher order of convergence in a weak sense. And the way to do this stuff is not difficult actually. So you just play with some moment matching conditions. So it's a relatively standard SD theory. Okay. All right. Okay. So let's see. There are some expressions here. So in the elliptic case, there is this guy here. It looks quite a lot like the term we get from the Milstein scheme. The hypo-elliptic case, there are some extra terms here that we have to take under considerations. All right. So that's it. Otherwise, if we want to actually, if you think in practice about how to simulate such a scheme, so there is one Brownian motion that it is the original one that comes from the SDE. There is this second independent Brownian motion that this scheme introduces. It's selected in a way, it appears in a way in the expression of the discretized scheme, so that some moments are matching the moments of the correct solution of the SDE. And there are these funny integrals that they are still Gaussian random variables. So there are essentially 4 Gaussian random variables included in this scheme. Okay, so it's nothing too complicated. They have these guys here. They have some dependency with the original increments of the Brownian motion, but it can be easily captured, this dependence. Okay, so you have a nice covariance matrix that it is explicit. So you can simulate this scheme. It's explicit. There's nothing complicated in it. All right, and the reason we have done all this effort is to increase the weak error here. Okay. So the weak error now, it has increased from 1, it has gone up to 2. The strong error is still of order 1. So there's no difference there. And I mentioned these moment matching conditions that you need so that you can try to increase the weak error, the order of the weak error. And there is a nice book by Milstein and Tretjakov that it shows it has some results that it shows exactly which moments you have to match to increase your weak error, the order of your weak error. All right, okay, that's it so far. I will show in a few slides some sort of a fast revision of the multi-level idea. So let's have a look. So what's the idea here? So you have a sequence of distributions that they go to the limit that you are actually interested in. So you are interested in an expectation under this limit. So this is the true solution of the SDE, let's say, at some finite, at some terminal time, capital T. And we want to approximate in a fast and accurate way expectation of the true thing. All right, in terms of if you want to do a standard Monte Carlo thing, you will fix some step size in your Euler scheme, for instance. And that's it, you will fix that, and then you will just get Monte Carlo samples from the terminal position. And that's it, all right? It so happens, that's the Giles idea. It's been around for many years now, that if you do some trick, you can do better than this simple Monte Carlo approach, okay? So somehow you can combine samples from all the levels of approximation. So let's say this is a coarse, this gets a bit finer, so smaller step size in your Euler scheme, smaller, and that's your final step size, okay? All right, just to make things extremely simple, as I promised here. So if we have this stochastic differential equation, so this is your step size at level L. All right. So now this level changes. So we can have different levels of approximation. So L starts from being small to being larger, all the way to capital L. And okay, so what's the trick here? If you do standard Monte Carlo here, the analysis is quite simple. So if you try to see how much effort you need to do to be within epsilon from the correct expectation of interest, so the analysis is not that difficult. So you fix your step size in whatever discretization scheme you have selected to solve your SDE. You have chosen this capital L, all right? So you have chosen this delta step size in your approximation scheme, right? And then you use some Monte Carlo samples. You average over your samples, and you do a simple analysis. So the mean square error. So this is the MSE here. So it's just the variance plus the bias squared. Okay. The variance plus the bias squared. This is where the weak error appears. So in the bias squared, this is the computational cost. This is the number of your samples, and there is a zeta parameter here that it's 1, for instance, typically for most optimization schemes. So how can we get a mean square error of order epsilon squared so that we are epsilon close to the true thing? So we have to control both the variance and the bias, the square of the bias. We have to make our step size to be small enough so that we control the bias. So that gives us a cost of 1 over epsilon for each Monte Carlo sample that we get. And then we have to control the variance as well. So we have to get epsilon minus 2 samples to control the variance. So in total, we get this, all right, epsilon to the minus 3, which is not entirely satisfying. So that was this is where the Giles idea comes into the context. So they say, all right, so let's look at the difference. Let's actually use the differences between schemes that use different choices of this delta step size. Okay, and let's work with this thing. So, right, this is a Monte Carlo. These are some Monte Carlo samples from 2 different levels, from 2 different choices of this step size. Okay, in the Euler scheme, let's say, for instance, or whatever other scheme, they should be quite close to each other if you do a careful coupling of these 2 random variables. Okay, if you choose, for instance, the same Brownian motion, both for the coarser level and for the finer level. Okay, so this should be quite close to each other. So maybe you don't need that many particles to control the variance of each of these quantities. Okay, that's the idea essentially. So that's the multi-level estimator, and that was the idea. So if you do an analysis here, so you have, because you have L of this term, the variance of the overall thing is the sum of the variances. Okay, and L here, this is the key thing. So you can select a different number of Monte Carlo samples for each of these differences. All right, so maybe you need a smaller number of samples as your step gets smaller and smaller. That's your computational cost. And okay, so this is where the things like the strong error of the solution of the ST becomes relevant. So this variance of this difference, it has some characterization. So it will be some power of the time step. So the time step to some power of beta. There is some computational cost again, and there is again some bias, right, involved in your estimate. In the Euler-Maruyama scheme, everything is equal to 1. So the weak error is 1. The strong error, this guy here, is 1, and the computational cost is always 1, in fact, in all the schemes that I'm showing here. Okay, and so this is the key quantity, the variance between 2 consecutive levels, and you can control this thing by adding and subtracting the correct thing. That's it, and using the strong error of the SD, and you can say, all right, that's order delta L. Okay, that's it. So something that I mentioned here is that in the antithetic multi-level, we will not add and subtract the correct SD, so it's a slightly different approach compared to the standard one in terms of controlling these variants. All right, and there is some constraint optimization. So at the end, this is the degree of freedom, how many particles you use at each level. And not surprisingly, so the smaller this variance is, the smaller the number of particles, and the smaller, the higher the computational cost, again, the higher the number of particles, and you do some constraint optimization, and you get a result like this. Right? So it's nothing difficult. Maybe I should just go on. Yes, this is in a nutshell the multi-level idea. I think the important thing that I will keep from here is that Z is 1. Z is the computational cost to sample from the approximate scheme to reach all the way to capital T. And beta is the strong error. Beta is the variance of the difference. Okay, so you have one level, you have one delta, you have the next delta, and you look at the differences. It should be close to each other, right? It should be quite close to each other. This is the important case. So if you manage to couple these differences in a way that this beta here that characterize this variance is quite big, bigger than 1, right? Then you're doing quite well. Then you have you capture you do the best you can do if you are using a Monte Carlo method, essentially. So you are within epsilon from the correct thing with an effort, with a computational effort, which is epsilon -2, right? Okay, this is, for instance, as if you are sampling, this would have been the same as if, even in the case that you could sample exactly from the original SD, okay, without any approximation error. Right, so let's see now where the multi-level, where this antithetic trick kicks in. So very simple, right? Black and lines and crosses, okay, so nothing more than this. So there is the coarse level with the green lines. There is the fine level that it just adds a point in the middle, okay? Nothing more than this. So that's the grid. I mean, I'm just introducing some notation here. That's the grid for the coarse level. So there's a difference there, if you remember, in all these calculations. So there will be one term in the difference will be using an approximation scheme over the green points in the grid. And then the other guy in the difference will be using the red points. Okay, so some extra steps. So 2 steps of the fine level will give me 1 step of the coarse level. Okay, all right. So let's see what it is that we are doing here. I'm working here with this scheme that we have introduced ourselves, this weak 2 scheme. So the weak error is of order 2, strong error is of order 1. We need something that it is more than 1 to get this optimal, this epsilon -2, right? So this is what we are after. So we want to get epsilon close to the quantity of interest with epsilon -2 effort. We cannot do that with a scheme that it has a strong error of 1, of order 1. We want to increase. We want to get a strong error of order 2. Let's see how it is that this is achieved. This is nothing more than a re-expression of this scheme that we have used. So yes, all right. So there is these were the terms involved in the scheme. The Brownian motion. This this guy involved these extra integrals, for instance, with respect to Brownian motion, some extra Gaussian random variates, nothing more than this. This was the guy that that creates this effect of increasing the weak error, the order of the weak error. It had this extra independent Brownian motion. But I'm just rewriting this approximation scheme, this discretization scheme that it was there also in one of the first slides. All right, and then what's the trick here? So you start playing around with the signs. Okay, so there is something called the antithetic version of this approximation scheme. So everything is the same, but the only difference is that this sign turns into a minus. Okay, but in terms of a distribution, you still have the same distribution. Given this guy is the same in both cases. The distribution of this guy is the same because there is an independent Brownian motion here. So even if you change the sign, but it doesn't affect the distribution of this thing. Okay. All right. So there is also the process on the fine grid. So an extra step to reach to do so 2 steps to make 1 step of the previous process on the coarse level. Okay, nothing strange here. We are just re-expressing this bar process is trivial. I mean, we just use we are just expressing this weak 2 scheme. Nothing strange is happening here. Then there's a second step. That's fine. So we go now. We do an extra step. So we reach the 2 steps of this at the fine level. It corresponds to 1 step at the coarse level. All right, and then there is again this antithetic process. So there's the bar process, and then there is this tilted process. So there is there's again a trick involved here. So what is happening here? If you notice, so we do this half step, and here there is some trick in the use of these increments. So we use the increment from the second step of the bar process. All right, and the same thing here. So in the first step of this process, we use the increment from the second step of this process. And the same thing here, plus we change the sign of this thing. This trick with the change in the order with respect to which you use this Gaussian increments. This is from the paper of Spruce and Giles. Okay, they have used it already there. I think something extra that we add here is the treatment of this term because it appears in our own scheme. And again, we use the same trick as in Spruce and Giles. And again, there is a switch in the sign. Tricks. Okay, there's no super deep things happening here. It's just a coincidence somehow that doing these tricks will cancel out some terms, and that's pretty much the idea. All right, that's the second half step, so that we reach also the 1 step of the coarse level. So the second half step of this antithetic scheme at the fine level. And all right, now we use the increments from the first step of the non-antithetic scheme. So what's the bottom line? Gimmicks, tricks here. So let's see what is going on here. That's the multi-level identity. So we are interested in, we try to find, we try to play around with this identity. And this method has to use an average of the regular approximation and its antithetic version, both for the fine level and for the coarse level, right? So it uses this trick. There are this plus in the one process, minus in the other process. There is these things that there is this switch in the order in which these Gaussian increments appear in the 2 processes. And all these things are going to make life, they are going to give something useful at the end. All right, let's control this. So this is the important guy, all right? So this is a guy that it should be, we want to have a small variance for this quantity here, okay? For the Monte Carlo estimate of this quantity, we want to have a small variance. So we need to find, we need to play around, do some error analysis for this difference. Okay, so we have introduced the average between the regular process and its antithetic version, both for the fine level and for the coarse level. And we start looking at this term. There is some standard analysis that it just uses a Taylor expansion, so it boils down to 3 terms. So here we want, so if for instance P is equal to 2, we want everything here at the end to be delta to the delta L to the power of 2, all right? So that will give us beta equal to 2, and that's it. Okay, it will give us a strong order of convergence of 2, and this is what we want to achieve. Okay. These terms are easy to manage, so we just use the strong error of the scheme. There's an extra 2 here, so there's no problem. This is the key term at the end of the day. All right, so yes, these are the simple guys, and this is the key term. So this is where all the tricks will become relevant. The change in the signs and the switching in the increments, blah, blah, blah. So indeed, if we get a result like this, we are done. So that's the theorem in the paper. So if this is 2, we get 2 here. So beta is equal to 2. So zeta, the computational cost, is equal to 1. We get epsilon error with the computational cost of epsilon minus 2. That's it. I mean, that's the main result in the paper. And just to see where all these signs and tricks are used. So if you look at the fine scheme, you get some terms like this. The fine scheme is, so what I have done here is that I have combined 2 half steps of the fine scheme so that it is comparable to the coarse scheme, all right? So that's the bottom line. There are some terms here that, because of these tricks, they have gone down to the residual term here. And then, surprise, surprise, yes, this is the regular scheme, and then this is the antithetic scheme, and quite conveniently, the things are the same. It's just there's a switch in the signs. So when I add these things and take the average, they will disappear, and that's fantastic. That's very good. And similarly for the, yeah, I mean, this is what has happened here. I have taken the average. Many terms disappear, and I get something extremely small. And also for the coarse scheme, so it's still the same. All right, and indeed, these funny tricks somehow that they don't come from some super deep, sophisticated ideas. They do the job, and you have a method that it started off by chopping off this Levy areas term involved in the Milstein scheme, but it still recovered in terms of getting accurate estimates of the quantities of the rest. It works as efficiently as if you could actually have used these Levy areas. Okay. All right. Okay, that's it. There are some results here. There is this. There's a Hypo-Elliptic scheme. There is this model that is used also in the Spruce, in the original Spruce and Giles paper. And indeed, numerically, it takes some effort when you use multi-level Monte Carlo in practice. You need to play around a little bit with the numerics. You need to choose a capital L level to control the bias. You need a constant in front of the number of particles, but you get things like this. So this pink, this purple thing is the good thing. It's the antithetic multi-level Monte Carlo. That's the standard multi-level Monte Carlo. And that's the standard Monte Carlo. So you're doing better. So the horizontal axis is the error, and this is the computational cost. And here we compare this thing. We have zoomed the plot to add another comparison, which is this Spruce and Giles stuff, the antithetic Milstein multi-level Monte Carlo. So the comment I will make here, and I'm pretty much done, is that in terms of analytical results, what we get here is the same as in the paper of Spruce and Giles. We have a higher order in terms of the weak convergence, and this makes a difference in practice, okay? Because in practice, you are not in the limit, so you have to choose a capital L. If you have a better weak error, then you can get away with choosing a smaller capital L to have the same bias, okay? All right, and this is the Heston model, and something that I will mention in the last 30 seconds, which connects with the theme of this workshop, which is about sequential Monte Carlo. There is a version of this multi-level idea with SDs. Also, when you use these SDs in a particle filtering setting, you have to do various couplings then there that they also involve the resampling, so it's very complicated. Thankfully, HJ has sat down and done the proofs. The proofs are there for the truncated Milstein scheme for the Spruce and Giles paper, not for this scheme that we have been using. It's not easy to come up with proofs, but at least we can see numerically that again this thing still works. There's an extra penalty that you pay in the filtering world. So the cost now is not epsilon minus 2, it's epsilon minus 2 times a log epsilon squared there. There's an extra penalty. It's all right. There are difficulties in life in any case. An extra log shouldn't make things much worse. All right, and again, yes, in a filtering context, so we see numerically that the cost is pretty much as we expect. So it's epsilon minus 2 with an extra log epsilon square at the front. That's it. Thank you very much.
Questions or comments?
No, the SD's discretization scheme is it's related to that commonly used one with like weak order 2 and strong order 1.5 or in your terms. So there's the well maybe so there's a commonly used one which has like a same weak order, but then a strong order is higher. So I was just wondering, so which has those Ito or Levy areas inside it?
Do you remember the name of the scheme or the name?
No, it should be.
You can't have something.
Okay, maybe it's not that, but like I see a benefit of this, I guess. So you get rid of the Levy areas which actually appear there. So you can.
Okay, and you still have strong error of order 1 and weak error of.
Yeah, because one is not very good for strong error, but when you are interested in the weak error, that's.
And it's explicit; it doesn't use the Levy areas.
But so I can ask myself, it's probably related to that approximation, but let's not go with that.
Yeah, it might be. Yes, might be.
Thanks for this simple talk.
It's good we were.
Yes. How behaves the error with respect to the time horizon?
For the filtering case you're talking about, right? Because the first it was the forward problem, so that was to fix the time.
Constant.
Yeah, yes. Yes.
Weak error does something also.
That's a good question, actually. Yeah.
For the strong ones.
For SDs in all these approximation schemes, even for the Euler scheme, right? I mean, there's nothing that I think there's something that explodes in terms of the time horizon. I think it's uniform in T, if I'm not wrong.
If you have some references, I will.
Yeah. Well, the only thing I can mention is the
Strong ones.
Yes. Yes, the strong ones as well, yes. The only thing I can mention is the,
It depends if the SD is ergodic. I mean, if the SD is ergodic, you can extend multi-level Monte Carlo to time infinity.
I think, of course, if the system is unstable, it will blow up.
Yes.
But if the system is stable, does there exist some literature on
Yes.
this subject?
Yes. For ergodic SDs, there exist a few papers.
You can give it to me?
so if it is ergodic, everything should be fine.
If it is
right?
ergodic, you actually do a double, level multi-level. You do multi-level both in time step and you also do a multi-level in the time of integration. You integrate the coarse level at time t and then the fine level a bit further or a bit below. I can point you out in the literature.
So for this approach here, something will go wrong with capital T. If capital T grows, something will go wrong.
Yeah, I think it should be the same. I mean, I think it's the same scheme, but because it's stable, it's uniform in time. I'm not sure we need to change the scheme.
Yeah, I'll be surprised also if it is ergodic. I'll be surprised.
Yeah, no, but yes, if it's ergodic, it should work, but there's the other, I mean, there's also, I mean, you also have another parameter to play if the system is ergodic. Yeah, how long you should integrate your system in order to, there's additional error coming from that one. And that's why you're also doing a multi-level Monte Carlo.
Because you talk about invariant measure approximation.
Yes,
But
exactly.
I'm just talking on a time horizon,
Okay. Yeah.
then it should be the same.
So what you're talking about is
Calculating an expectation with respect to calculating an ergodic average.
you're looking at the computational cost also in terms of capital T, isn't it? Is what you're
Yeah,
saying.
but for an ergodic average, not for a finite time approximation.
Yes.